for our next talk, Ariana Hoppelman and Brian Hill, and the topic is Stepping Stones for TFOP, Experience of the St. Mary's College Geissberger Observatory.
Actually, I'm Chicken. Oh, Brian Hill. So, we're at St. Mary's College, Geissberger Observatory. Up there on the right is our dome, and that's where we teach undergraduates. We have a bunch of stuff in the container there, and hidden just over the edge of the hill is the campus itself, and we're about a half hour east of San Francisco, just east of, as you can see, the first range of coastal hills. And our talk today is Stepping Stones to TFOP, and you heard about this from the angle of the head recruiter, Dr. Christensen, this morning, and so now you're going to hear about it from the angle of the eagerly recruited, that's us. So actually, it's a bunch of really tractable steps, and that's our outline, and we're going to go through it one step at a time. They're tractable, but there's a lot of details. So the first step began 2 years ago at the conference that was outside of Boston, the 105th meeting of the AAVSO, and the theme of that conference was the age of large surveys. And there were a lot of just like beautiful and inspiring talks there. There's a few titles. 3 of the titles that I put up that were really amazing were about these huge telescopes that were going to survey the entire sky that was visible to them, and they were so agile they could do that every night. And 3 more of the talks that are there were specifically about exoplanets. And at this point you might hang your head. If there are absolutely huge telescopes that can survey the whole top sky that's visible to them every night, what's left for us? But the message was that every one of these surveys is actually limited in one way or another by what it can do, and the demand for follow-up observing is ever, ever higher. And so after that, we were just really inspired. As a specific example of this, there's again what you saw this morning, the 4 cameras, each pointing 24 by 24 degrees, in grand total taking up 24 by 96 degrees. Each sector, that constitutes a sector. Each sector observed for 27 days. The southern hemisphere will be observed in 13 sectors. Well, the downside of that, if you're looking at that much sky, is your pixels are pretty big. So that's actual imagery from our gear, and you can see a lot of detail inside that square. And that square actually represents a single test pixel, which TESS would see as a single shade of gray. So, if the dimming is on one of those stars versus the other of those stars, ground-based observers with relatively modest gear can help figure that out. So we left the conference really excited, and fortunately, Dennis Conti was teaching the Exoplanet Choice course. That's one of the AAVSO's many series of courses. I took that course in February from him, and that left us not just excited, but knowing a lot more about what it would actually specifically take to gear up to do differential photometry. And we kind of foundered there at St. Mary's a little bit because we needed to raise some money to upgrade our 16-inch scope. And then along came an awesome student, and I will hand it over to her.
Sounds good. Hi everyone. Thank you. I've never used mic. Anyway, hi everyone. My name is Ariana Hoppelman, and I came to St. Mary's in the fall of 2017 as a freshman. And then in the spring of 2018, Jessie Christensen came to St. Mary's and gave a talk about her new project called TESS. And I was immediately interested in it, and I asked Brian how I could help St. Mary's join the follow-up program. She told us that our gear was ideal for exoplanet research, as long as we could perform differential photometry with the accuracy and precision necessary to see exoplanet transits. So, in the summer of 2018, just this past summer, I went through Dennis Conti's course materials, as Brian had, and then we started taking images of eclipsing binary transits. We started with eclipsing binaries because we could find targets that experience light drops in the tens of percents compared to the exoplanets' ones of percents. So they were much easier to identify. They also occurred more frequently, and we could find much brighter targets typically. One of our best transits was 00AQL, which is a MAG 7 star in Aquila. We took just over 1,000 pictures at 6-second exposures over about 3 hours. And here's a picture of me taking the data. It's very cold. There we go. As per Dennis Ponte's choice course, we calibrated and analyzed the pictures in AstroImage J. Picture. You can see our target stars highlighted, as well as a few comparison stars, and then we managed to produce a light curve. In this light curve, we have the target star curve plotted twice, once temporally binned on the top, and then unbinned, and also our comparison stars are at the bottom, layered on top of each other. What we saw was, as expected, a 50% drop in light, which is very encouraging because it meant we could successfully image eclipsing binary transits. Concurrently, we were also updating our imaging train and our mount. We have a 0.4 meter niche Cassegrain telescope, which is currently sitting in our dome. And we upgraded the mount from we upgraded the Paramount ME mount from the RS-232 electronics to the USB electronics, which are the most current. Here are some images of us managing to get it in and out of our lab, which was very difficult because it is insanely heavy, but we did it. Concurrently, we also updated our imaging train. We got a reducer flattener, an autoguider, a CMOS camera, a temperature compensated focuser, a USB filter wheel, as well as 5 new filters. We got a blue Barker filter and then 4 of the Sloan filters, the G prime, R prime, I prime, and Z prime filters. We also got a new flat field pen, which allowed us to take more consistent flats than dome flats or sky flats do. Here is a very nice picture of all of it set up in our dome. Once we had finished all of these upgrades, we were at a good point to start taking images of exoplanet transits. We started with known exoplanets using public databases to find our candidates because we were more concerned about being able to match results that were already achieved. And these were harder targets than our eclipsing binaries, but not as hard as the targets we'd be getting from tests. One of our best data runs was Stress 2, which is in Draco. It is an 11.4 binary star system. We took about 500 pictures at 15-second exposures over 2 hours, and we managed to get a little light curve. We saw the predicted 1.6% drop in light, which is much less than 50%, but we still saw it, which is very encouraging because this perfectly matched the data that we were able to find in the NASA archives. At this point, we were feeling very good about ourselves, and we decided it was time for us to try and apply to TESS, to their follow-up program. The application materials are laid out on their website, which is up here. You need to include a statement of abidance with their policies, as well as sign the NDA. You need to indicate your subgroup interest. We chose subgroup 1 because that was the most appropriate for the data that we had. You need to describe your background and your expected contribution to tests, a description of your instruments and your observatory, the instrument availability, as well as your local team availability. And once you have all this information together in a PDF, you send it off to them and you will hear back from them. Once you're accepted to TESS, you will get access to these 3 databases as well as the TESS observation coordinator, and you can use these databases to find appropriate targets for your location. The first 2 targets you take data on will be priority for known false positive targets. The purpose of doing this is to demonstrate conformance to the TESS standards for data submission. The priority for target we chose was actually from the CELT catalog. It was a 10.9 mag star. We took 800 pictures at 20-second exposures over about 5 hours. We actually took this data at the Barcroft Field Station in the White Mountains. We had an opportunity to go there at the end of the summer, and we wanted to take advantage of it. Once you have your data, you will submit 9 different files to the TESS database. These include a full field view, a zoomed-in field view, a plot configuration file, as well as a measurements file, among some others. This is our plot for the data that we got at Barcroft. We observed a 4.5% drop in light, and after we submitted this data to the test database, Karen Collins reviewed it and informed us that this was consistent with what the CALC team had found, that analyzing the fit parameters of this curve indicate that if there was a planet orbiting this specific star, it would have to have 5.3 times the radius of Jupiter, which is well above the typically accepted upper limit of 2.5 times the radius of Jupiter. That is consistent with the planetary interpretation. So it is definitely not a planet. Now I'm going to turn it back over there.
So our second false positive target to demonstrate conformance to the submission process was also from the CALC catalog. And this star has VMAG 11.4, and it's that one that my shaking hand shows as T1. Now here you'll see that we chose 5 target comp stars, which are those 5 red ones, well away from the target, because the suspicion was that there was contamination of the target star. And all those other green ones are additional target stars. So we got the data, we analyzed it, and sure enough, in this case, the top line up there represents the target, T1. And this line with the wild variation, in fact, it's so wild it has been compressed by a factor of 2 so that it doesn't dominate the plot. This line with the wild variation is actually T3 in that plot, so I'm going to go do a blow up of that. So there's T1 with right there again, and there's T3. And T3 is 3.7 magnitudes dimmer and 40 arc seconds away. And so what's happened here is this very large variation in T3 has been sort of slightly folded into the variation of T1, thereby creating a false positive. So we submitted this, and we got reviewed and feedback, and actually this is on the basis of ours, and observations like ours is permanently retired from the CALC false positive catalog. So that's actually where we are today. I want to look ahead, because TESS is surveying the southern hemisphere, and we haven't actually done any test targets. And so just to understand that, just a little bit more detail, there's a mismatch between ecliptic north and the Earth's north, okay? And TESS, when they say TESS is surveying the southern hemisphere, TESS is surveying the ecliptic southern hemisphere. So there's a little band over here where TESS is actually going to do some positive deck targets. And in the next few months, that's what's actually going to be happening. So here out of the TESS schedule of operations is exactly the dates and the coordinates that the cameras will be trained on. The one that's up in the upper left, I'm sure you can't read that, so I'm going to read you the important things. That's Sector 4, which just happened. It had a deck of minus 2.76. Sector 5 is the first one that's going to have positive deck on its northernmost camera. Sector 6 gets all the way up to 5.4 degrees positive deck. Sector 7, we started to fade back into what we think of here on Earth as the southern hemisphere, so it's back down to 2.5. And in Sector 8, it'll be at minus 4. So what you're going to have right over the next several months is, for us northern hemisphere centric people, apologize to the southern hemisphere people who might be here, for us northern hemisphere centric people, there's a sort of a trickle of targets that are low on the horizon. And the real bonanza begins in Sector 14. For us, that's when TESS starts doing sectors 14 to 26. 14 to 26, we'll start getting that flooding into us in the fall of 2019. And so, like, the wonderful message for people here that have been thinking about this for quite a while, but maybe some reason or another didn't take the plunge, actually, there's still most of a year to take the plunge, to train up, to gear up, to go through the acceptance process, to do the false positives, and at this conference next year, you'd be sitting in the middle of basically a flood of new data. So that's very exciting. Other than a few sort of like epilogue things, that's where I want to leave it, but I gotta thank the people that funded us. So there's 2 sources of money that helped us with all the gear upgrades at St. Mary's College. I also gotta thank the manufacturers. They did not just sell us the gear. Every time they sold us gear and expertise.
because every observatory is totally unique, and the fact that our image train is set up properly is thanks to the help they gave us after they sold us the temperature compensated focuser. And so there's a nice list of manufacturers that helped us out. And then I also got to thank the researchers. The overall idea that there'd be this survey satellite and then maybe like 100 teams around the world that were feeding into TFOP subgroup 1, that's a beautiful idea for sort of crowdsourcing exoplanet research. And then I want to thank two researchers specifically, Dr. Christensen, who's here, and Dr. Collins, who's the head of subgroup 1. Both of those people gave us not just like, hey, yeah, encourage you, come on. They gave us actual specific onboarding help. The final group I want to thank is the AAVSO community. If it weren't for that conference 2 years ago, we'd probably still be scratching our head on what our observatory is really good for. And if it weren't for Dennis Conti's course, we probably would have been a lot slower on the uptake as well. If you can't take Dennis's course, there's a whole pile of online resources. His way is the fastest way to get through the material, but there's a whole lot of online resources that will let you do the same thing. And I want to say on online resources, Bob Buckheim from SAS told me at breakfast this morning that he's actually going to lead a webinar with a lot of interested people in early December. And we are, of course, always love to give back to the community by answering questions or even driving to your observatory if you get stuck on some random detail. Thank you.
Okay, thank you, Brian and Ariana. We have time for questions.
Just go back one slide.
Go back one slide. There you go.
You want a picture? Okay.
I just want to make an announcement, simply because you pointed out how important is all this support that we get from the community, and part of the community are these individuals who are building filters, building instruments, and making sure that our community has the right gear to do this kind of work. So Optical Structures Astrodome was just told me that they're offering 50% discount of all photometric filters until December 1st with the code AAVSO. So I didn't tell you earlier because I wanted you to pay attention to that, not what we're talking about. But something to keep in mind, okay? It's through the online store.
When you check out, you can enter the code. And then you get it through December.
Okay.
Stella,
All right.
was it 50 or 15?
15, one
I'm curious, if you can say any words about how you did the data reduction with sort of software package or anything like that?
Yeah, well, by the way, I'll say those 5 filters that were up there, which were the CBB and the G prime, R prime, I prime, T prime, are your Optical Structures Inc. Filters, the Astrodome. In answer to the question, why don't I let you tell them how that, oh, you didn't hear the question. The question was, what exactly data reduction software are we using?
We're using AstroImage J. What's the answer? Okay.
I think that's all you're really looking for
We're
is
using
AstroImage J.
It's really good in the sense that it does everything. You can upload your lights, your flats, your darks, your biases. You can have it create master biases for you, and then it'll create the calibrated images that it'll save in a different directory. You can open them and you can align them. You can align them manually, or you can have it align through its software. But if there's some drugs, you can also do that manually, like from inputs and stuff like that. You will perform differential photometry in the same software, and so there is another module by which you can do that. And then it'll produce a measurements file and also a light curve, like the plot that you saw. It'll produce that, and also a few different windows by which you can customize your plot, what you want it to show and how you want it to show it. You can temporally bin your data. You can have it show you the error of your data. You can have it produce different sort of fits for your data, depending on if it's a comparison star or a target star. And it'll tell you how good the fit is. It will not give you residuals on your parameters specifically, but it will tell you the how close your fit is to the actual data, and also give you error on your data points.
And I'll just say it's not required to use that, but you gotta realize Karen Collins is fielding stuff from 100 different observatories, so if you wanna make your life easy, either use that or make your work products look just like that.
Could you talk about the camera that you used in your calibration process?
So, budget played a big factor. So, and I did mention, or actually Ariana mentioned, that we're using CMOS cameras, okay? And we have some ideas there on how we can do well. For differential photometry, almost everything that you could possibly be interested in washes out. The only thing you might really have to worry about is nonlinearity, and our counts were pretty low. So I guess we haven't studied the properties of our camera a lot, and we chose it to be relatively inexpensive, and people would probably say that the fine pixel scale of CMOS is a mismatch to our long focal length classic Schmidt-Cassegrain, but we've been 3x3, and because we're binning 3x3, that means we're using 9 pixels on every given sort of super pixel, and actually that's turning out to give us really, data that's sufficiently clean that it's kind of opening people's eyes a little bit, that maybe CMOS actually is a pretty good, not just a budget way to go, but a pretty darn good way to go.
And I think we'll hear more about that later. Any other questions?
It's a ZWO ASI 1600 mm cool, which goes for about $1,300 and has been superseded by the same thing with the Pro designation, but it's pretty much the same thing.
Any other questions?
Hi, where did you get your flat fielding panel? Can you say a little bit about that?
It's a Jared Newman flat field panel, and we ordered it online.
Yeah.
And we built a little holder so it could go over the telescope, which we did ourselves. They don't sell that, but actually for the 0.4 meter scope, the panel actually fits directly on the scope, and so you don't need to worry about it falling off or anything. It fits it perfectly. For the smaller scopes that we use for the eclipsing binary data, I had to build this little slot for it to slide into, and then you could slide the telescope into one end. But yeah.
Can you repeat who that's from? Because this is becoming kind of a widespread problem to get access.
It's Jared Newman.
Okay.
I could.
And they're called Aurora flat field panels.
Almost there.
And I'll say,
There you go. If you want to take a picture, it's okay.
we basically followed Dennis's directions on that. He said you're going to get better results if you get a flat field panel. So we just went that direction, and we don't actually know that personally how much better or worse our results would be. And so we had the luck that we could spend quite a few $100s to get one of those flat field panels for a good size scope.
Okay, another question?
I'm developing a little student course in digital imaging, and I'm curious what you think as a student the learning curve is on learning the software processing. Is it something that can be done in a short time, or do you really need a semester length of time to do that?
It's tough, but it's possible. Okay, at the beginning of the summer, the only thing I knew how to do with a computer was maybe write a Word document, and make a PowerPoint. So it was definitely now I can use Terminal, which is really exciting, and GitHub and all of these fantastic tools that I had no idea how to do. So it was definitely, I'm talking to someone I couldn't do anything, and I learned it all. Granted, it took about, I think, a solid 2 weeks for me to figure out how to take the eclipsing binary data. But that was spending maybe 6 or 7 hours a day on it. So I think doing it in a semester would be entirely possible. I've also, looking back, I think it would be entirely possible for someone to do this in a semester. It is hard, but it is not impossible. I'm a good example of someone that did not know anything about anything at the beginning, and now I know quite a bit. Yeah, no, it's definitely.
You have to have a student though that's
willing to beat their head against obstacles, okay? If you have a student that comes to you every time they get stuck, you're gonna be basically in full-time software education mode.
Any other questions? Well, thank you again. Very much.